Hello friends, this is the second part of the first lecture on subsurface characterization and classification. If you have not watched the first part, I would recommend that you do and then come to the second part. So in this lecture, I'm going to talk about the type of soils that are out there. As you may know that we have two types of soil. One is a coarse grain soil and the other one is a fine grain soil. So what really constitutes a coarse grain soil? The coarse grain soils, you could see the individual soil particles with no difficulty. And that is not the case with the fine grain soil. The soil particles are extremely small. And I'll tell you how small is extremely small. Now, coming to the second concept associated with soil classification, although it's not a direct part of the soil classification, but I would like to include it here as opposed to later because I would like you to know what is cohesive soil and cohesionless soil, because this is going to tie in with the future discussions I'm going to have on the lectures. So what is cohesive soil? Cohesive soil is just a sticky soil, and that would generally be a property of silts and clays. And for cohesionless soil, as the name would suggest, that it doesn't have any stickiness associated with it. So silts and clays are cohesive, sands and gravels are cohesionless. And I'm going to talk about the poor water pressure and other effects that actually causes the cohesiveness in the soil. But that's a discussion for other day. Now, what do you think about silt? Is it cohesive or cohesionless? And it's actually a loaded question because in my practice, I've seen many engineers classify silt to be a cohesive soil by default. Well, that is not true because pure silt has no cohesion. In nature, however, silts are generally present in the form of silty clay, which actually gives them the property of cohesiveness, which is why many people classify silt to be a cohesive soil, but that should not be by default. And I'm going to discuss more about this in the near future. Now let's jump onto the topic of soil classification. So here I'm going to talk about the USCS, and the other classification is the ASTO. In my practice, 8 out of 10 times I've seen that people have used the USCS classification. It is the most widely accepted and practiced classification system, which is why I'm going to present that in the lecture here. So essentially what we have done is we have broken down the soil particles depending upon the sieve size. So what is happening here is any soil that gets retained on this number 4 sieve soil is essentially gravel or cobbles or boulders, depending upon how big the soil is. Well, I have seen boulders in my practice that are as big as a truck. So those are not uncommon either. But for the purposes of this lecture and for your understanding, I'm just going to say that the soil is classified based on the sieve sizes here. And these sieve sizes are standard because this is the standard produced by the USCS system. You can pause this video and go through this table, but essentially I'm going to describe it in the next slide or two as to what they actually mean. So as you can see here, this is the distribution of the soil. So what is happening is we are pouring the soil sample on this first sieve, and then this entire stack is put on a shaker. This shaker actually shakes for like 3 to 5 minutes on every increment. And what we are doing is calculating the quantity of soil that is retained on each sieve. And this is what this table signifies here. So this number 4 is this 4.75 sieve. So out of all these sieve sizes here, I would say that you should memorize these 4 sieve sizes: number 4, number 10, number 40, and number 200. As I said, number 4 is 4.75 millimeters. Number 10 is 2, number 4 is 0.425, and then number 200 is 0.075. And among these four, this number 200 here is by far the most important sieve size, because this is what differentiates between the coarse grain soil and the fine grain soil. So when the soil retained on this number 200 is greater than 50%, it is a coarse grain soil. When the amount of soil is less than 50% on this number 200 sieve, it is a fine grain soil. So if anything, try to memorize these four sieve sizes: number 4, number 10, number 40, and number 200. Between number 4 and number 10, you have the coarse sand. Number 10 to number 40, you have the medium sand. And from number 40 to number 200, you have the fine sand. So sand is ranging all the way from number 4 to number 200. Above number 4 is gravel, and below number 200 is silts and clays. To have a further distribution of silts and clays, you would have to do the hydrometer analysis. And I'm going to talk about hydrometer analysis in the next lecture too. So as I said, basically what we are doing is we are putting the soil on the top sieve and then putting this entire arrangement on a shaker, shaking it for 3 to 5 minutes. They all look like cake pans. But what we are really after is the amount of soil retained on each sieve. And after we have obtained that, what we generally plot is this percentage passing versus the grain size distribution. And I'll tell you why it is important to do this, because we would like to discern between the behavior of the soil as to how it relates to the particle size. So what you see here, the Cu and the Cc value, is this is the uniformity coefficient and the coefficient of gradation. And I'll tell you why this is calculated in a bit. But for now, just keep in mind that this uniformity coefficient relates to the particle size. You may ask, what is D60, what is D10, what is D30? So what we are talking about is a grain size. You see this D60 here? What we are after is a grain size corresponding to 60% passing. So when 60% of the soil passes, what is the grain size? That is the D60 value. Similarly, we have D10 and D30 here. So based on this grain size distribution curve, we have the uniformity coefficient and the coefficient of gradation. We have D60 over D10, D30 square over D60 times D10. And I'll tell you what these values signify in a bit. So you see the percentage finer versus the particle size, we have three behavior of soil types. One is poorly graded, well graded, and gap graded. It means that in a well graded soil, we have soil particles ranging all the way from 0.002 to almost 20 millimeters. So it has a long range of soil particles. Therefore, we call it a well graded. Now, in case of a poorly graded soil, it only means that the particle sizes are pretty limited, as you can see here. Similarly, in case of a gap graded soil, it means that there are few particle sizes that are missing. And why do we need this? Because we need to classify the soil. In order to determine whether it is a well graded soil or gap graded soil, we need to determine the uniformity coefficient and the coefficient of gradation that I discussed in the last slide. So these were the formulas that you have to use: D60 over D10 and D30 square over D60 by D10. Well, the people who came up with the USCS system, they wanted to classify the soil based on numerical values and formulas, and they never wanted people to just eyeball it, which is why we have these numbers here. So when the uniformity coefficient is greater than 4 and when the coefficient of gradation is between 1 and 3, it is a well graded for gravel. And when the uniformity coefficient is greater than 6 and the coefficient of gradation, I beg your pardon, is between 1 and 3, is a well graded sand. If it doesn't come in this category here, it's a poorly graded sand. If it doesn't come in the category here, it's a poorly graded gravel. And I'll tell you about this distribution more, so be a little patient. As you can see here, when the percentage gravel is greater than percentage sand, it means that the amount of soil retained on number 4 sieve is greater than the amount of soil passing the number 4 sieve. We have to use this flow chart. And depending upon the amount of soil that is passing the number 200 sieve, we could classify the soil further. So when the percentage gravel is greater than percentage sand, and if the percentage fine is less than 5%, that means the amount of soil passing the number 200 is less than 5%, and if the uniformity coefficient is greater than 4 and the coefficient of gradation is less than 3, then it's a well graded soil, that is a well graded gravel. So as you can see here, the description given is GW. So in case of USCS system, the behavior is the second letter and the principal soil type is the first letter. So if it's a well graded gravel, it's written as GW, and if it's a poorly graded gravel, it's written as GP. Now you may ask, what are these dual symbols here? Now these dual symbols are used when the percentage fine is between 5 and 12%. So when you see that the percentage fine passing the number 200 sieve is between 5 and 12%, you're going to see a dual symbol. And depending upon the uniformity coefficient and the coefficient of gradation, you're going to see the dual symbols, whether it is poorly graded or well graded, depending upon that. Similarly, when the percentage sand is greater than percentage gravel, and depending upon the amount of soil passing the number 200 sieve, and depending upon the CU and the CC values, you could actually classify the soil further, whether it is well graded or poorly graded. And the same principle, that is when the percentage fine is between 5 and 12%, there would be a dual symbol. So basically, if I were to summarize this lecture, what we're really after with the grain size distribution curve is the percentage sand, the percentage gravel, the percentage of fines. At this point of time, we are not after the percentage silt versus the percentage clay. That's a part of the hydrometer analysis. But for now, what we are trying to determine is the percentage classification, the soil classification as it pertains to the coarse grain soil. So as long as you have the percentage gravel, the percentage sand, the uniformity coefficient, and the coefficient of gradation, using these two